Hello, and welcome to another Fun with Physics with Uncle Bob. This week, we'll be taking another look at a problem in structural engineering before we leave that field. Specifically, we'll be dealing with the problem of multiple joists lined up along here atop a girder or beam or purlin or rafter down here. This top view would be the elevation view from the side with our multiple joists sitting atop the beam. If we look at a plan view or above, we'll see this with joists here and so on, and our beam or purlin here supported on each end. It's important to note that between each joist and our beam there will be a force here, 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 here that will deflect our beam and also deflect each joist. This force is acting up on the joists and down on the beam. The problem is the deflection of this beam at midpoint, where stress would be greatest, is determined by each one of these forces of the joists pushing down on it. So it's a complex problem. If we look at this situation from the end, looking in this way, we'll see this, or possibly this, with our joist above, beam here, here. Sometimes towards the end of our beam support here, we'll see actually a downward deflection here of our joist. More towards the center, we'll see more of this situation with our beam here and joist deflecting in this manner. So it's a complex problem. The solution to this I'll describe next. Here's that program I wrote in Power Basic to solve this problem. First thing I'll do is let you see the entire program. If you want to copy it, feel free. Move it down. There'll be 2 pages. Page 1 and page 2. And that would be it. We'll go back to page 1, where we'll look at this situation of 10 joists supported by one beam or purlin. The right half of this beam symmetrical to the left half. In other words, each half of the beam supporting 5 joists. We'll just look at and analyze the left half, one half of this beam with the 5 joists. The upper portion of the program, there's user input of physical characteristics of the joists and beam and so on, and spacing, as you see here, self-explanatory. One of the methods we'll be using is a superposition of the forces on the joist that will account for the joist deflections. The uniform load at the top of each joist will force each joist downward, and there will be a point load due to the beam contact on each joist at its midpoint, at the joist midpoint, forcing it up. These forces, along with each joist support forces, will account for its stress and deflection. Each joist spacing is given here, user input. We come down. One of the keys to this program is a manual entry or manipulation of the forces on each joist between that joist and the beam, where that force will be pushing upward on the joist, downward on the beam, and you will manually enter and play around with a lower limit and upper limit for each of these forces along with a step size until you get an output of this program that where each force will lie between the lower and upper limit here. At that point you can reduce your step size if you want to narrow it in even further. Down here we'll see the traditional deflection equation. This will be for the beam, and this is where we calculate beam deflection due to these 5 joists. The second page will carry on with this. Up here. And so the next key to this program is that what we're looking for is a deflection downward on the beams equal to the deflection downward of the joists at each joist point contact on the beam. So in other words, at joist midpoint where it deflects downward, that deflection must equal or be very close to the deflection of the beam at that point for each of the 5 joist supports. Next, we're going to look at some outputs of this where I can explain this further. Here's that program. We'll run it in 3 cases with these 2x6 joists. We'll do a case each of a 2x8 beam, a 2x10, and a 2x12. This is the 2x8 beam, as you see here. I'll go ahead and run it, and we'll look at some output very quickly. Thumbs down. Here we are. And hopefully we can see the top of this, but we've got 5 rows for each of the joists, as you see here. And the first thing we'll notice is that we're looking at only the left half of this symmetrical beam. The joist stress with no beam support would be 1257. Notice that we've got 1257 down here and a beam force of 0 on these middle joists here. This indicates we've lost contact between the joists, these 2 joists, and the beam at this point. Again, joist 1 would be the leftmost or joist closest to the end of the beam. 4 and 5. 5 would be the middle or close to the middle joist. So this is significant, probably not a good situation to have with this 2x8. What we'll do is run this again with the 2x10 and see what that does. So here we have the 2x10. Now I'll go into this a little more detailed. Notice that our beam forces here must be between our lower and upper limits on our program that we manually set for each joist, and they are in this case. This is the first thing to check. The next thing is to look at our beam deflection and joist deflection, which should be very close to the same. As you see, they are. We notice that our joist stress on our first beam from the left is a negative, indicating a downward curving joist. Same here. On our third joist, it starts to curve upwards. The important thing is our maximum stress, as we would expect, would be towards our middle or fifth joist, and that is 1180 curving up. But we really haven't gained much, because if there was no beam support, there would be 1257 at that point. What we'll do now is go on and run this with a 2x12 and see how that does. Here's the 2x12. Again, the first thing to check is to make sure our forces here are within or between our upper and lower limits that we set manually, and they are in this case. Notice that our maximum stress has moved from the fifth joist up to the first. Here we've got a minus 1064 in our first joist, a downward curving joist. And again, of course, 1257 would be the maximum with no beam support whatsoever. So whether this is good enough for your application, you'd have to decide. The point is, you have the procedure to use this in your own situation, and maybe it could be of use to you. So that's enough for this time. Next week we'll be going on to a different field entirely. So we'll see you then on Fun with Physics with Uncle Bob.